In this video, we'll be looking at a binary called SF. This binary was actually presented at one of our CTFs at my university. So I want to use this as an opportunity to kind of look at it and figure out an exploit for it. So here I've actually copied this binary into the protostar system. You can usually do this using SCP. Just SCP it into the root directory under root permissions. Root permissions are the username is root and the password is godmode. Okay, so once you have the binary copy, you can of course change the permissions to run as root. This will make it more fun, and you'll be able to see it run as root whenever you exploit it. What does the binary kind of look like? Well, let's go ahead and take a look. We're going to go ahead and drag this into IDA. So we'll go ahead and bring it over and just drag it down like this. Okay. As you open the binary, you can see a lot of things are kind of going on. The disassembly looks quite busy compared to the ones that we've been seeing with protostar, but essentially, one thing that pops out the most is these addressing rows here, where we have an address relative to EBX, as you can see. So what is going on? Well, if you look at how EBX is initialized in this program, we have a push EBX, which arguably saves the calling procedures EBX register. But after that, we call a function called x86 get thunk is equal to EBX. And what this does is it moves the contents of ESP plus 0 into EBX. What does that do? Well, remember when we call a function, we move the address of the following instruction in the current running code into the stack. So essentially, when we add this ESP, this is getting the value of the next address. So in other words, it's going to put this address 0804871 into EBX. And when we add 18FF to EBX, what does EBX become? Well, let's go ahead and look. If we look at 8701, and then we go to and see that this leads us to the global offset table. And this global offset table is essentially what we are seeing with EBX. So EBX will actually be set to the global offset table. Why does code do something like this? Well, sometimes you want to write position-independent code, and especially if you have any experience writing code that can be code snippets that can be loaded into any program, you will see that the code needs to be relocatable. To have relocatable code, you need to have some certain things constant. In this case, we have access to the global offset table. So as you can see, anytime we access a pointer, like standard in or standard out handle or a string that's located relative to the global offset table, and in the data section, we go ahead and use that relative addressing. Okay, so going through this program, we see that at first we have called the set vbox, this is pretty standard, and then we have a rep stars. Now, this basically copies the value of in EAX into the address points for EBI. In this case, EBI points to a buffer in the stack here, located at 5C below EPP. And we copy 0. So basically, this is zeroing out a buffer area. ECX contains the count. In this case, we have 16. So we're zeroing out 16. D is double words, so 16 double words in the buffer. Okay, after that, we move a bunch of values into this. So as you can see, we change this. We can see that this spells out answer. So essentially, bump from 0 to 8 is going to be answer. Right. So I'm not exactly sure what's going on here, but let's continue. So then we have what we call the puts on guess my favorite food. Okay, so as you can see here, we're again using the addressing, and IDA is smart enough to know that we're referencing via EBX. After this, we have to call to read of 55 bytes into buffer, in this case, exactly this buffer that we cleared, except now we have an answer. But if you look closely, at what we're doing, we're actually taking buffer but then adding 8 to it. So this is actually reading a string plus 8, which is incidentally right after this pretext here. So we need 55 bytes from, in this case, FD0 with the standard in, and then we go here and we actually print it out. And if you notice, we print out the entire buffer, including the prepending thing. But essentially, this is vulnerable. Because essentially, we're just calling printf on this buffer that we just supplied. So this would be something to watch out for. And especially when you're going through these larger binaries, you want to find weak points like this. After this, we call string length on a string that is in the pure data section. In this case, it is to return it to a string. It is Shellfish with Dr. Pepper. This is string length, and the string is Shellfish Dr. Pepper. And then we compare what is in our buffer up to the string length of this string, which we can easily check here. It's 2.4. This will always be 0.4. We're going to check the first 24 bytes of our buffer with this, and then we test it. Okay, so if it matches, we go here. If it fails, we go here. Okay. Or sorry, the other way around. If it's not zero, go to fail. Yeah. So this is actually success. So if there's a match, we go over here. If there's a failure, this just looks much easier to analyze. What we do is print out a message. Actually, I don't care. And then go here. If we succeed, then we go through this much longer but more interesting routine. So in this routine, what happens? Well, first we give it a quick congratulations, as opposed to actually I don't really care. And then we call memset on, in this case, Bob. F is your 0. So what could this mean? Well, essentially when we end with this kind of bit mask, we're just clearing out, in this case, the last 12 bits. So we're aligning it to 12. The memory region size to be 12. Okay, so that will give us buffer. But remember, buffer is on the string. Okay, so EAX is point to something on the string. I'm going to subtract 4 from ESP to get ready for this function call. And we're going to then set, and look, the character is C. So we have another min set here essentially, but it wasn't done in the same way. It was done later in the coded, in the assembly itself. We're now using memset, but we're using, we're putting 0 into the character because this character is a character. It's not a word. But interestingly enough, we have a word here. So what this will actually do is just 0 7 bytes, starting at whatever this address is. Okay. Then we call string length on this again, which will get a 1. And then we're going to add 824. And where will this put it? And then we're going to add the ESI. ESI is that extra block. To this point, ESI will point to this block after. Whatever starts here is what we're going to do. So if you can imagine, if we just input the string and press enter, we're just going to have ESI pointing to, let's say, This value is loaded in the front above, and that's no factory X, and then we call the X. Okay, so this here is another vulnerability because notice that we directly control what's happening on the screen. So when we call this, we basically can run our own code. And if you note the name of the challenge, it's called SN, or in other words, Shellfish. Right? So this should be an indication that we're looking for something that will actually require us to write some shellcode. Okay, so after we call the AX, we put that into the return value, and then we jump to here. Here, we add 1 to the counter, which was, you can see, is initialized to up here to 0. And we compare it against 2. If it's less than or equal to, we go back. So as you can see, this loop actually runs for 2 plus 1 or 3 times. After that, we call print shell, which seems to just print a picture of the shell, as you can kind of see here. And then we get our standard exit. So this part here is just like our stack integrity, and so on. Okay, so now going back through this code, we can see that essentially there are 2 different vulnerabilities that we could build. We can either try to exploit using printf, or we can try to exploit using the shell code here, the fact that we get to directly control the code that's executing in the AX. So which one will it be? Well, if you notice, the limitation on the shellcode is that we can only write 55 bytes total. That's not including the string here, which we saw has 24. So that really leaves us with only 31 bytes of shellcode that we can do if we're going to use this path here. Well, is 31 going to be enough? It is. The shellcode can actually be very small. All we need to do is run exec.de sh, and then we're good. So let's see how compact we can get that code, and then if that works, then we can just go ahead and use this approach rather than using the printf, which we know to be a little bit more involved. So let's open Notepad, and let's write what function we would like to call. So we want to run exec.de sh, and parameters we don't really want to assign to the program name, and we don't really want we don't really care about the environment either, so we're just going to do it like this. Okay, so now that we have this, we got to figure out how we can actually call exec.de, because we're not going to find the address out of the loaded libraries. We're just going to use a system call. So if you go to the Linux syscall reference, you can see here, syscall number 11 is exec.de. And exec.de should be very familiar in terms of the operation. We just execute essentially a program in path name and supply it with the argument of argv. The first argument of argv, of course, has to be the program name itself. And we don't really care about other arguments, although if we wanted to, we could include them. Okay, so the first thing we want to do is create a stack that will allow us to kind of create this kind of structure. If you take a look at this for a second, though, you notice that this is a pointer to a character constant. This is a pointer to a set of pointers, and this is a pointer to null, or a pointer to another set of pointers, but we only have one pointer that is null. So we want to get a pointer to null here. How can we create such a thing? Well, the first thing is, well, we can see that this is really just a subset of this. And in fact, if we just see that it's the later path. So we can really create this structure here. And notice also that null has the value of 0, and 0 also happens to be the terminating value for string. So really, we just have to worry about creating this structure, and we can take different pointers, parts of this structure, to create, to fill in our register arguments. As you can see, when we do syscalls, we don't really use the stack to push arguments. We use the registers. Okay, so the first thing we'll do is kind of create this, and we'll start with this node. So one of the first things you want to do when writing shellcode is to not use any null bytes, because as you know, when we read values in, uh, sometimes using a fread, the null byte will terminate the read. So we would like to avoid it if possible. So this will clear EAX, and now we want to push this value onto the stack because this will create this null. Okay. So at this point, what needs to point to a null pointer? Well, uh, EDX does, right? EDX is the third argument. So this is EDX and sets EDX. So we move EDX with P. Okay. Now what do we want to do? We want to push the value of VSH. Well, what is the value of VSH? You can see here, you can kind of arrange this, and then we can generate board C for the students. And let's make that a little bit easier to read. So let's put it in this. Alright, so now we can see what we need. And we want to remember we have to push it kind of backwards because the buffer will be bounded. So this needs to be the highest address. And this is the lowest address. So if we want to write this out, we want to first push this part here. Remember, H is the highest address. So we want to start with 638 and then 73 here. And then we want to push this here. Okay. Again, the highest value should be N, and the lowest value should be this one side. Okay. So that comes this E, this 9, this 2. Okay, so after this is done, we can now go ahead and we push this on the stack. So now this structure pretty much is complete. Now we still need a pointer for both EVX and ECX, but they're pretty much the same. Because they both essentially, you can have them both point to, well actually this is not true. You can move it back to SP, right? But what I should have said here is pointing to NSH. Okay, so let's change things a little bit. So, okay. Right now, essentially what we have is BNSH, which is BNSH in the null. It looks like we need some. Let's go ahead and push. Okay, so currently, let's try to move ESP into EVX. Okay. Now EVX points to the string, and we want to push EVX. To the point, push another null. So I think this will work. So what we're doing is our stack will look like this. At the very top, we'll have a location we'll have a null, and then we'll have sh. No. Okay. And actually, if I may, I'm going to actually move this. Not that it matters, but I'm going to go ahead and move this here so that in this case we can actually make it a little bit more consistent. So this is the actual string located here, and this is the pointer set. So this structure is equal to this, and we have so at the end of this we have EDX pointing here. We're gonna have oops, we're gonna have EDX CX pointing here. This is our P, and then our EDX is just going to go here. The programming. Okay, so this is our shellcode. Now all we have to do is put it into shellstorm. Yes, shellstorm, we definitely need that. So let's go ahead and put that similar. Alright, so this is our shellcode. Remember, we'll use our which is Shellfish. I'm going to put this at the end. So before we take a look at how long that is, let's go ahead and see what the length of our shellcode is. You see the length of our shellcode is 25, and the length of this part, remember, well, I'm just going to leave 24. So the total length of this is 49, which is well below the 55 limit. So this should work. Let's go ahead and try it out. So to do this, we're going to echo without new line and escaping bytes. New line is single quotes. After that, I'm going to go ahead and cat to keep the pipe open. In order to keep that set. I'm going to put the string in. And after we put it in, you can see we got congratulations when it first checked the string. Check the first 24 bytes of the string, but everything after that basically got executed directly. So if we go and now execute QMI, we can see that we essentially got an SH to row. Okay, so that is pretty much it for this video. I hope you enjoyed, and I'll see you in the next exploit.